Okay, I just started recording. Okay, so the idea is that the solutions of the Laplace's equation and Poisson's equations are unique with respect to boundary condition. And that means if you can find a shortcut or somehow give a guess what the solution could be, if you try that solution and if that solution satisfies the boundary condition, satisfies the Laplace's or Poisson's equation, that solution is the only solution. Okay, so you are done with solving the equation. All right, so a question is that how do we know that the answer is unique? Okay, so we looked at two different situations and we proved that the solution has to be unique. Otherwise, if there are two solutions, those solutions should be identical and exactly the same. Okay, so one case was when we are in a situation that we are in a space that has no charge distribution. So we are inside a volume that the potential should satisfy Laplace's equation, okay? And on the boundary, we have the value of the potential specified. So V is specified on the boundary. Okay, so what we did was we tested and we said, let's suppose there are two solutions, V1 and V2, okay? And then we looked at the difference between the two. We said, let's define another function, potential, which is the difference between V2 and V1, okay? So if you define V3 like this, then we reason that V3 has no choice other than being zero everywhere. And that means V1 and V2 should be the same, okay? And the way we came to that conclusion was that we said if V1 and V2 both are satisfying the boundary condition, then V3 on the boundary condition must be zero because both of them are satisfying the same boundary condition, so the difference between that must be zero. So first of all, we said V3 is zero on the boundary, and then we said inside the volume, V3 also satisfies Laplace's equation, okay? Because V1 satisfies Laplace's equation, V2 satisfies Laplace's equation, and then the difference between the two should satisfy Laplace's equation as well, okay? And look at V3, what kind of function it is. It's zero on the boundary, and Laplacian of that is zero everywhere, okay? So it has a flat boundary, zero everywhere, and inside that is flat. So there's a trivial solution for this equation, and that is V3 is zero everywhere, okay? So this is the idea. If hypothetically there are two solutions, we can look at the difference between the two solutions, and difference should be zero, meaning that there is no way we can have two solutions for. So there should be one unique solution to the Laplace's equation. For this case, where we have V potential specified at the boundary, and inside the boundary, we do not have any charge distribution, okay? So this was one case. This was a simple case. And there was another case that we looked at, in fact, the Poisson's equation, okay? And that was a volume that we have certain charge density. We also have pieces of conductors, okay? You can have as many as pieces of conductors that you wish. And then you can also have some charge distribution on these conductors. They can be neutral or they can be charged, but the assumption was that they have certain charge that could be, of course, zero, but certain charge on the conductors. So you can imagine a situation like this. You have these pieces of conductors, and on each of them you have certain charge. I'm going to say QA, QB, QC, and QD, okay? And between the conductors, you can have certain charge distribution as well. All right. And then there is one more boundary condition around that encapsulates everything. Okay, so this boundary condition can be small or can be hypothetically very, very large, meaning that extending to infinity. Okay, so this situation covers a lot of possibilities that we have charge distribution and conductors, and we have a boundary condition that could be all the way far away from the conductors and charge distribution and become zero. Okay, so in this case, we looked at the electric field, and we showed that electric field must be unique based on how much charge we have on the conductors, what type of conductor distribution we have, and whatnot. Okay, so the way we did this, it's a little lengthy. I'm not going to go into details, but again, we said, let's suppose we have E1 and we have E2, both the solutions for this problem, okay? And we then look at the difference between we define E3 as the difference between E2 and E1, okay? So we look at this difference, and then we apply the Gauss law, and then we look at a few different things, and we showed that the integral of E3 to the power of 2 over the whole space must be 0, okay? So there were a number of steps to come to this conclusion. I'm skipping those, okay? We discussed that on Tuesday. We came to the conclusion that integral of E3 to the power of 2 times d theta should be 0, okay? And if you have such a positive integrand, right, so e to the power of 2 can be either 0 or positive, okay? So if this integrand over the whole space is 0, that means E3 must be 0 at every single point in the space, okay? So again, this is one of those conclusions that you make assumption that there are two solutions, look at the difference between the two solutions, and you conclude that the difference must be 0, okay? So for this case, that covers many type of possibilities of having charge distribution combined with conductors. Again, we showed that the electric field is uniquely determined based on the boundary conditions and charge distribution, okay? So these are fundamental in the sense that after these proofs, we know that in any situation, if we can somehow come up with a solution for a Laplace's equation that satisfies boundary conditions as well, we are done with solving the problems, okay? No one can tell you, okay, this was easy, do another way and find another solution, okay? So as soon as you come up with the answer, and that's it. Any questions so far? Is this more or less clear, the concept here? All right, so we got 19 students here. Cool, okay, so following this, I want to give an example of an image charge. So there are two types of image charge problems that is studied in the textbook. I'm going to do one of them that is a situation that you have a conducting, infinitely large conducting plane, and you have one single point charge near that conductor, okay? The question is what type of electric field, what type of electric potential, and surface charge induction we have from that system, okay? So let me erase.
Professor?
Yes.
I just wanted to let you know, I don't think the recording for the class last Tuesday is up yet.
Yes, because I didn't get a chance to upload it. A bit of technical problem. The way I'm recording the video and audio are separate. What I need to do is that I need to edit them in a software and then export and then upload, okay? And the file became so big, it's near 20 gigabytes. I could not upload from home. So my plan today is uploading it actually today.
Okay, thank you.
Yeah, we have the recording, it's gonna be uploaded. Okay, so the method of image, this is a classic problem on image charge. Okay, so imagine we have a conducting surface like this that extends all the way to infinity. Okay, and then we have a charge of, let's say, Q at a distance Z above the surface. Okay, so what you can imagine is that because it's a conductor, okay, it has mobile charges. And if you put the charge Q here, a lot of charges will be induced on the surface. Okay, so the charges opposite to Q will be gathered close to here, and then like charges gonna go far away. Okay, so we have charge induction here. If Q is a positive charge, we will have a lot of negative charges here. And as we go far away, we're gonna get less and less negative charges. Okay, so to start with, can you guess what type of field line we're gonna get from this sort of charge distribution? Have you seen this problem before? Yes? Okay, so let's go step by step. What kind of electric field line do you expect for this problem? Imagine Q is positive. It doesn't really make big difference, but for the sake of simplicity, let's imagine Q is positive, and we are getting negative charges here.
Well, it will only be in the Z direction, right?
Is only gonna be in Z direction? No. We will have curved field lines. How do you think, like, what is your first step if you want to guess what sort of field lines we have here? What is the first thing you do? Okay, I can tell you what is the best way. Okay, the best approach is this. If you have multiple charges or point charges, okay, so what you do is first you just go to the place that you are super close to the charge distribution to have. So it could be the point charge or it could be the conductor. Okay, so go very close to those charges. And what is going to happen is that if you are very close to each of these charges, the effects of other charges are minor and the field line is solely determined by what you have right now. Okay, and that means if I go very close to the charge of positive Q, okay, I'm going to erase this one. If I'm very close to this one, okay, effect of all other charges in the whole world becomes irrelevant, and field line is only determined by this. Okay, and if I have positive point charge like this, I'm going to get field lines that go like this. Okay, so this is the only point that is creating these charges, is these field lines, and then those field lines are diverging from the points.
And so would they, is it like this? Like do they go down and around?
Yeah. Okay, so on this point is like this. How about on the surface of a conductor? What type of field line do you expect?
Going up?
Going up, always perpendicular to the surface of the conductor, right? So you remember that. It's going to be always perpendicular. Okay, so on this one, we get field lines like this. And we can imagine that if the positive charge here, we're going to get higher density of negatively charged here. Okay, so probably we get more field lines here, and then as we go away, we're going to get less of this. Okay, so near this charge, we get this, near conductor, we get this, so then we need to somehow connect these to each other. Maybe like this. Then get other things like this. So this is the sort of field line we get when we have one point charge near a flat conductor. Okay. If the conductor was curved, it would have been a little more complicated, but if you want to qualitatively draw the field line, you can just follow the same thing. On the surface of the conductor, this should be perpendicular to the surface. Okay, and near any point charge, it's just uniformly diverging from the point charge or converge. Okay. right, so now how can we, so this is so far it was a qualitative discussion, right? How can we really calculate what type of field line we have? The best way is just looking at the electric potential first. Okay, so there are different ways. There's one easy way here, and that is we create another situation that satisfies the same boundary condition that we have. Okay, so the boundary condition that we have here is that on the surface of the conductor, electric field is zero. Right, this is one boundary condition. The other boundary condition is that if we go all the way to infinity, so far away from the system, because we have this point charge, electric field again becomes zero. Okay, so electric field is zero at the limit of r goes to infinity. Let's imagine r is distance from the point charge or anywhere near this. Okay, so we have these two boundary conditions. Okay, and then within the volume, above the conductor, the equation is a Laplace's equation. The Laplacian of V is zero. Of course, we have a point charge here, but that is only one single point. Beside this, which is infinitesimal small point charge, the rest, we have the Laplace's equation that needs to be satisfied. Okay, so.
Professor,
Yes.
is it supposed to be the limit of E equals 0 as V approaches infinity?
Limit of, no, electric potential V is zero as we move all the way to infinity.
As V, but it said as V goes to infinity, V equals 0? No?
As R, this is R,
Oh.
and then any distance
Oh,
from
okay.
the point charge. Is it clear?
Yeah, sorry, I was just confused. Sorry.
That's fine.
Professor, why, I just want to make sure, why we're using the Laplacian in this example?
Because we don't have any charge distribution, we only have one single point charge. Okay, there's no rho, there's no volume charge density, so the Laplacian becomes zero.
Okay. Thank you.
Except right at the point that we have this charge distribution. That's too small, we don't need it. Sounds good?
Yes.
Okay. So basically, if we want to calculate potential above here, we need to solve these, and then with these two boundary conditions, and with the assumption that we have one point charge here. Okay, so that's the whole thing we want. Okay. So method of image has very interesting suggestion, and the suggestion is that instead of solving this problem, let's look at something which is very simple, and that is, let's eliminate the conducting surface. Okay, let's imagine a situation that there is no conducting surface, but we have the same charge of Q at the same position Z. Okay, so we have the same charge of Q at position Z, no conducting surface. Instead, let's imagine we have a charge of negative Q on the other side at the position of negative side. Okay, and it says that if we solve the electric potential for this system, which is easy because this is a system of only 2 point charges, the same electric potential in the above is going to satisfy the boundary conditions and the Laplace's equation that we have in this system. And it has a point charge the same way that we have a point charge here, and both of them are Q, right? And so the solution of the potential in this problem applies to this problem as well. Okay, so this is the suggestion of the method of image chart. Okay, so now let's look at this. Qualitatively, if you want to draw the field line on this, you know the field line between a positive and negative charge, they look like this. Right, and it's very symmetric, right? It's very symmetric, and the symmetry is nice because we know that right on the surface, where Z is 0, the field lines are going to be perpendicular to the surface, all of them. And that's somehow consistent with what we expect happening on the surface of a conductor, okay? So now what we need to do is that we need to write the electric potential that we get from this system and see if that electric potential really satisfies the boundary condition here as well. Okay, writing electric potential for this system is not that difficult because we have only 2-point charges, right? So you can write electric potential at any position. I'm going to write on the top Vx yz. That is created by one positive charge sitting at one charge Q sitting at plus C and one charge negative Q sitting at negative C. So if I want to write in terms of the distance from these charges, distance from the positive charge, I would say is a square root of, at any point in a space with xyz, I would say x square plus y square plus z minus, I think I better choose another distance other than z because it gets confused with the coordinate system. So let's use plus d, and that is consistent with the textbook. Okay. So imagine you're sitting at plus d and negative d. So z minus d squared. So this is basically the distance of every single point in space from this charge q. Okay. So any point at xyz has this distance from the charge q, and I'm going to call that r positive, and r negative is very similar except that the charge is sitting at negative d, so it becomes x2 plus y2 plus z plus d squared. Okay, and electric potential becomes 1 over 4 pi epsilon 0 q divided by r plus 1 over 4 pi epsilon 0 q divided by r minus. Okay. So this is the electric field that we get. By the way, this is negative q, so I rather write it as negative here. Okay. And if I want to substitute this r plus and this r minus here, I'm continuing here, I can write it in terms of x, y, z. We get q over 4 pi epsilon 0 times 1 over a square root of x2, y2, z minus d square minus one over square root of x plus x2, y2 plus z plus d square. Sounds good? So this is the electric potential that we get for 2-point charges above and below this plane. Okay, so now I want to test if this exact electric potential satisfies the boundary conditions here. So if we go at infinity, x, y, and z are going to be very big numbers at infinity. So both of these two terms inside the bracket become 0. So v at infinity becomes 0, and that's a good thing. And how about v on the surface of the conductor? Surface of the conductor is where z is equal to 0. Okay, so if we set z at 0, what we get is that we get x2 plus y2 plus d squared in the denominator of one term, and we get x2, y2 again, we get d squared, the denominator of the other term, and we are here, we have a negative sign, so at v equals 0, we get this one as well. Okay. So this equation satisfies both the boundary condition, and both are the solutions where we have 1 point charge Q sitting at plus D. Okay. So this solution satisfies everything that we want for a system that has a conductor, okay, that has an infinitely large conductor and a point charge near it. Sounds good? And this is actually confirms that we came up with the answer. The electric potential and electric field above this conducting plane is exactly the same as the electric potential and field that we get from 2 point charges with this sort of arrangement. Sounds good? Okay. So one thing now we can calculate is the density of the induced charges on the surface. Okay, so I put negative signs with the assumption that this is positive, but it could be negative, then we just get oppositely charged positive charges here. Okay, so that doesn't change the generality of the problem much. Okay, so
I have a question, sorry.
Yes.
So you found the general formula, right? That it works also for the values underneath the x-axis.
The value underneath the z-axis.
Where the conductor is, right?
Okay, so if you have a conductor, okay, you don't get any charge distribution, any field line or anything here. Okay, everything's going to be zero here. Okay?
But the equation still works for that.
The
right?
equation works for that because the equation is written for potentials right here for 2 charges. Okay.
Okay.
For the case of conductor, just ignore anything below 0.
Okay.
And just focus above 0.
Okay.
Okay. So now that we have the electric potential everywhere, there is a way to calculate the density of the induced charges on the surface. Okay. How do you go about that? We know that the surface charge density is proportional to the discontinuity of the electric field, right? So if you remember, we had equation that sigma, the surface charge density, should be proportional to epsilon times dV over dn to the negative sign. Okay, so we had this when we look at the discontinuity of the electric field, and for the case of the conductor, because there's no electric field inside, we only have electric field outside, so the sigma should be equal to the electric field right above the conducting surface. Okay, so in this case, the perpendicular component is z, so this is equal to negative of epsilon 0 dV over dz. Okay, so this is what electric field component can be related to the surface charge density. Okay, so what is V? V is defined by this, okay? And then in order to calculate the electric field, we should take the derivative with respect to Z in the denominator here, okay? Okay, so I'm gonna write that's a long derivation. So by the way, this is done at z equals 0. Okay, so dv over dz is 1 over 4 pi epsilon 0. Okay, so I'm going to say q here. The first term gives us, so the first term, the derivative gives us z minus d over x2, y2, z minus d squared, everything to the power of 3/2. And the second term gives us z plus d over x2 plus y2 plus z plus d squared to the power of 3/2. Okay, so this is the derivative of v with respect to z. To calculate the surface charge density, we're going to look at that at z equals 0. Okay, so if we set z equals 0, that becomes a lot more simple. So at z equals 0, it's q over 4 pi epsilon 0 times negative d over x2 plus y2 plus d2 divided by 3/2 plus d divided by x2. Let me see. This has to be negative, by the way. This has a negative sign here. So this becomes positive, and that becomes positive as well. x2 plus y2 plus d squared to the power of 3/2. Okay, so it becomes simple in the sense that the denominators are now the same when z equals 0. Okay, and then if we combine, that becomes 2qd over 1 over 4 pi epsilon 0, 2qd divided by x2, y2, d2, power of 3/2. And if we multiply this by the negative epsilon 0, negative epsilon 0 cancels out this epsilon 0, and that is going to be the sigma that we have. Okay, so if you look at this, the sign of the sigma is opposite to the sign of q. So that means if you put positive charge, you're going to get negative charges induced here. If you put negative sign, you're going to get positive charges induced here. And that makes sense, and that's what we expected. Another thing is that if you move from the center here, okay, the further you move, the larger x and y you have. So the further you move, you get a smaller and a smaller charge distribution. Okay, so if you want to plot the density of the induced charge, sigma, as a function of distance from the center, we're going to get something like this. Right at the center, where x and y are 0, we get the maximum induced charge density. And as we go far away from the surface, we're going to get a smaller and smaller charge density. Okay, so this is going to be technically the magnitude of sigma with respect to, let's say, r being the square root of x2 plus y2. Okay, so everything makes sense in the sense that we get oppositely charged induction. We get an induction of oppositely charged ions, and then as we move away from the center, we get a smaller and smaller charge distribution. Okay.
Can you
So,
explain why it's negative again?
Because that's what we expect. If you put positive charges, you expect negative charges induced here. The attraction is between opposite charges, right?
So just because of the picture, we wouldn't know that just calculating it, right?
Even from so qualitatively, that's what we expect, right? If you put positive charge, we expect negative charges come closer to that because of the attraction. Okay, so that's the qualitative or conceptual view. But when you do mathematics, you expect to get the same thing in the mathematics as well. Okay, this is just consistency check. You expect to get a negative sign here so that the sigma and q are opposite to each other.
Okay.
If that makes sense. Okay. So now that we have sigma, we can actually integrate the sigma over the whole surface all the way to infinity. And if we do that, we're going to get we're going to get the total amount of negative charges. Okay, so it's 1014. I'm going to stop here. Next week on Tuesday, I'm going to start from here and from this sigma, and we're going to calculate what sort of total charges we have here and what is the real physical attraction between this Q and the surface of the conductor. Okay, so I'm going to stop here and give you 1 minute to breathe, and quiz is going to be online at 10:15. Sounds good? If you have any question from this, you can ask now. I'm here.
I have a question. It's related to the distance r. I know what it is, but I just want to know related to the distance when you derive the potential.
Okay.
And I just want to know how is it the square root of x squared plus y squared plus c minus d squared. I know what it represents. I just want to be able to see it.
Oh, that's going to be technically the distance. So if you look at this in 3 dimensions, okay, so imagine this is your plane, and this is the charge that is above this point, okay? So r is going to be the distance from this point, okay? If this is q, this is a projection of the q position on the surface. This is r, which is a square root of x2 plus y2. And that is right here. So this combination here is r squared.
Oh, okay. Okay.
Cool.
Okay, thank you very much.
Good. Okay, I'm going to open the critique web page and just to make sure that the quiz is online. You guys should be able to see the quiz right now. Do you see it?
Yep, it's online. It's up.
Okay, good. Do you want me to give 1 minute brief explanation on what the quiz is?
Yeah.
Okay, let's do that.